Welcome to the 18th lecture of Logic and Distributed Control System. So today we are going to discuss about the PLC sequencer function. So these are the objectives. At the end of this chapter, you will be able to describe the operation of electromechanical drum sequencer, compare the operation of a PLC ladder program with a PLC sequencer program, and describe the basic PLC sequencer function, apply a timing sequence to a PLC sequencer operation. So as an introduction, the PLC sequencer function is often called the drum controller function. We use the function designation as dr instead of sq, which has already been designated for the square root. So PLC sequencer function will be designated by dr because the concept was originated from the drum controller function, which is a mechanical device, or electromechanical device, we can say. The sequencer concept has evolved from the mechanical drum switch, which is an important control device, but the PLC sequencer function handles large sequencing control problems more easily than the drum switch. So the drum switch, what the drum switch is, we are going to understand that one, because then only the PLC's advantages of PLC sequencer function as well as how it is working, it will be clear. Another advantage of the PLC is that its sequential programming is relatively straightforward and user-friendly. The traditional drum switches are manually operated. If a timing of steps being controlled by the drum switch is required, manual operation time by a clock is needed. But in case of PLC sequencer function can operate between steps by programmed time sequence. This chapter explains how the PLC sequencer function operates and can be applied to the control problem. Let us try to understand that one. So this is the typical electromechanical sequencing operations which is done by drum controller has been shown. The figure shows a small electromechanical drum controller. Here you can see that two important things we can observe from this figure, that is that it has some motor, okay, and here you can see this these are the one knob you can see, or you can see a joystick or jockey, okay. So now we are going to know how this drum controller, which is an electromechanical device which is now replaced by a PLC sequencer functions, how it is going to operate, that we are going to know. So we introduce some terminology associated with the drum instruction by describing the original mechanical drum shown in figure, okay. The mechanical drum generally has pegs on its curved surface. Peg means some projections will be there on the curved surface. Let us see. So this is the drum, okay, and you can see that on the surface of the drum some projections are there, or which is known as pegs. Pegs are there. So now the pegs are populated in a particular pattern representing a set of desired actions for machine control. So these pegs are in a particular pattern. So here the peg is present, but here it is not present. Here it is present, and then you can see that 1, 2, 3, the three positions the pegs are absent. So these are in a typical pattern. Pegs are inserted on the drum to execute some desired actions for machine control. A motor or solenoid rotates the drum a precise amount at a specific time. So in a specific time this drum is going to rotate, okay. So rotate maybe in this direction, okay, but at a time it is going to rotate in a step, fine. So now let us see that what are the other points. That is, during the rotation, stationary wipers sense the presence of pegs, which is if it is present, it is on, or it is absent, then off. Then you can see that at a particular position, here you see the wipers are there. At a particular position, if this pattern will come whenever the pegs are present, then there will be a contact. Okay, connections will be there. Where the no pegs are present, there will be no contact. So with this, whether it is contact means whether it is on or whether it is off, with that the circuit to operate the machine will be completed. So that's why the interaction makes or breaks electrical contact with the wipers, creating electrical outputs from the drum. The outputs are wired to devices on a machines for on-off control. So this is the way the electromechanical drum is going to operate. So here most important thing is that at a time, at a specific steps, it is going to rotate. So once it is going to rotate the full rotation, then the total number of steps will be executed. Okay, so the drum usually have a finite number of positions within one rotation called steps. So each step it having a particular pattern. Okay, each step represents some process step, means it is going to suppose we have 16 machines to on or to make it on and off. So depending on that in what time what pattern we want, depending on that the pegs will be present. Fine. So at power up, when we will switch on, the drum resets to a particular step. The drum rotates from one step to the next based on a timer or some external event. So that's why in a electromechanical drum sequencer, you will find that this knob or these joysticks is present. So maybe manually also we can perform the steps. Okay, but it will be good that if there is a timer, and that will take care the execution of each steps. During special conditions, a machine operator can manually increment the drum step using jog control on the drum's drive mechanism. The contact closure of each wiper generates a unique on-off pattern called a sequence and designated for controlling a specific machine. But here you can see that the drum is circular, and because of it automatically repeats the sequence once per rotation. So one rotation if it is complete, and whenever it is going for the second rotation, the same pattern is going to repeat. Applications vary greatly, and a particular drum may rotate once per second or as slowly as once per week. So depending on your requirement, this rotation you can control that each step will be executed by per second or it may be per week depending on the application. Okay, so now here you can see that the pictorially a table has been shown. Suppose we are going to control the 16 outputs and we are going to control it in a different pattern with the 16 number of steps. So this will be the chart from which we can see that what are the pattern to make the output on and off. So you can view the drum as a chart as shown below. Each row represents a step and numbered 1 through 16. Each column represents an output numbered 0 through 15 to match watt bit numbering, and the solid circles in the chart represents the peg, means it is the on state in the mechanical drum, and the open circles are empty pegs, that is the off state. Fine. Now suppose this drum sequencer operation we want to perform using PLC sequencer function, not with these electromechanical devices, because here already I have mentioned at the beginning what are the disadvantages of mechanical drum switch. What are they? Once again we can repeat that is, traditional drum switches are manually operated. If a timing of the steps being controlled by the drum switch is required, manual operation time by a clock is needed. Okay, and the PLC sequence function can operate between steps by program time sequence in comparison to that. Okay, so this is the greatest advantage when we will go for the PLC sequencer function, which is exactly same thing going to do using what the drum sequencer is going to do. So So now we will try to understand how the PLC sequential function will be useful with respect to contacts and coils arrangement. Let us do that one. So to begin the discussion of PLC sequencer, a simple sequence of the operation is shown in figure. Three lights, suppose lamp A, B and C, are to be in the on or off state in 5 consecutive different combinations. The 5 steps are to be in a given sequence 1 through 5. A1 indicates light is to be on and 0 is off. So ABC, light ABC at step 1, light A will be off, B and C will be on. So at the steps 2, some pattern will be followed. Like that, the step 5, some particular pattern has to be followed by the lamp A, B and C. Okay. So now suppose we want to perform or we want to develop the PLC programming using contacts and coils. So let us try to understand with the physical switches first. Okay, so solution is that the required light pattern sequence of figure can be accomplished by manually opening and closing the 3 toggle switches as shown in the figure. Figure shows that open or close status of the 3 toggle switches for each of the 5 required sequence patterns. So suppose at the first manually you are doing that L1 must be means for the A switch must be off, B switch must be closed, for the C switch must be closed. Like that manually you can do the operation, or you can go for the contacts and coils arrangement. How you can do that one? As an alternative to using toggle switches, the 3 lights could be connected to the output of a PLC using coil contact system as shown in the figure. So let us see how it is going to operate. So we have the A, B and C lights and 3 switches, the 5 combinations we have OR it. Okay, now suppose this will be the sequence that at the sequence number 1 only IN001 will be closed. If the IN001 is closed, it means that B and C is at the step 1, B and C is going to glow but A is going to off. In the step 2 only IN002 will be on. If the IN002 is on, so this will be on as well as this will be on. So means at that time B is going to off, A and C is going to on. So it is going to maintain the sequence desired sequence what we have fixed. But it is convenient when the number of inputs and number of outputs are in a small number. What does it mean? Number of inputs means, what I want to say that number of steps are small. So that's why now suppose that instead of a 3/5 sequence, we have to program 14 outputs on up through 47 steps. So using toggles or a PLC contact coil system for control would be a long and complicated system. However, programming the system with a PLC sequencer function is relatively easy. A PLC sequencer function is shown in the figure and which having 3 inputs. So this is the PLC sequencer function. As I said that it will be not indicated by SQ, it will be indicated by DR because it is keeping the name of the mechanical drum sequencer, so DR. Now you can see that 3 switches are there: IN001 which is the step circuit, IN002 with the resets which is used for the reset circuit, and IN003 which is used for the enable circuit. At most interestingly, what are the things is needed to declare? The number of steps, how many number of steps you are going to perform. Here for example it is given 11. Then the starting register, that is 101, where the what is the meaning of HR101 starting register? Means starting from the HR101 along with other 10 registers where the pattern will be written, okay, in which pattern you want to make the particular output on and off. And the step pointer HR100 means it will as the sequence will go stepwise, the pointer will move to that particular register to indicate that which register is now active. Then each of the pattern, when it is executed, the output is transferred to the designated register, that is the output group register, that is 002. So let us try to understand how it is working. That's why the step circuit, each on pulse steps the function to take to the next HR pattern. So here, as I said, that HR 101, so it means that HR 101, you will write the particular pattern what you want to execute. Okay, so like that, HR 102, you will write another pattern. So now each step it will move from one register to the another register to execute that particular pattern, and that status is going to transform to the OG002 such that you can control the particular output pattern. Okay, so reset circuit, each on pulse resets back to the first HR, and enable circuit, when on the function may be step but not when off. Okay, so when enable circuit is on, then only this function is going to be operated. Okay, so here the sequencer function block is programmed with 4 pieces of information. What are the 4 pieces of information? Number of steps to be sequenced through, as I mentioned, that is 11. The starting register used for the sequence, where the starting register 101, it means that if you indicate the number of steps, so it means that consecutively 11 registers will be there where the pattern is written. The step pointer location on HR, that shows which steps you are on, and the designation is the OG register, a group HRs that are controlled on and off by the sequencer function. Okay, so now we will try to understand the previous example, that is 3 lights and 5 steps are there, and the 3 lights has to be on and off at a particular pattern. The figure shows how the PLC sequencer function could be used for our 3 light system and 3 light 5 pattern control. Okay, after the function is programmed, the on-off bit patterns are inserted into the registers used in the sequence. You see, so we will write the step 5, the starting register, suppose 601, and the pointer initially is starting from 600, and the OG001, the output group register. And at the 601, you will write the first pattern, and 602, you will write the second pattern, 603, third pattern, fourth pattern will be written 604, and the fifth pattern will be written at the 605. Then what will happen? Now once you will pulse the sequencer function, then and each pulse, the first pulse, what will happen? Now the pattern 601 will be executed. In the second pulse, if you give the pattern of 602 will be executed. So like that, if you apply the fifth pulse, it will reach to the 605, and once it will reach to the step 5th, the last step, which is going to execute the pattern of 605, at that time only the DR or CR16 is going to be energized. At the last step, it is going to be energized. That is very important to remember, because it will be useful when we will do the programming. Okay, so that's why here it is very much clear from the discussion that the programming for more steps and outputs would be done similarly. For example, a 47 step program for 14 outputs would have the first function in the block programmed with the number 47. The specified start register could be anywhere. There are 46 more unused registers following, and if 601 is the starting register, then the series involves registers are 601 through 647. The pointer and OG groups lines in the blocks are programmed as required, and then the appropriate bit patterns have to be put into the 47 registers, that is HR601 through HR647. As the sequencer function operates, the output DRCR16 only comes on at the last step of the indicator. Means whenever we will going to perform the 47th number of steps, at that time the indicator is going to be on. Okay, So now we will discuss a one example where you can understand a basic PLC sequencer application with timing function, because that is interesting, that how the timer will be involved with the sequencer function such that each steps can be controlled by the timing function. So for we further illustrate the use of sequencer function by applying it to control of a dishwasher. We are going to take the example of a dishwasher problem. We assume that the dishwasher has 6 functions that must be turned on and off periodically on actual dishwasher. So like that, what are the steps you have to perform? Now, soap release solenoid, then the input, these are the actuation you have to do. Soap release solenoid, then the input valve for the hot water, such that you want to make it on such that the hot water will come. Then wash impeller operation, wash impeller should rotate, then after rotation, then drain water valve should open, then drain the water, then drain pump motor should be controlled, and heat element for the drying cycle has to be completed. The operational pattern for the dishwasher has been shown. Suppose this particular operations in each step has to be performed in this pattern. So there are, suppose we want to perform 11 number of steps, okay, and we have the 6 number of outputs. What are they? Now the dry heat element, then the drain pump, drain valve, wash impeller, water in valve, and soap release. Okay, so first step, what you have to do, you have to release you have to open the water in valve. So that's why this cross mark represents the on, and all other things must be off at the first phase. And you will find that total 11 phases are categorized in this way, that first 3 steps are known as pre-rinse, and then 4, 5, 6, 7 is wash, and then 8, 9, 10 is rinse, and 11 step is dry. Okay, so at the first step, what you have to do, that water in valve should be on, other things will be off, and step 2, the wash impeller should be on, other things must be off. At step 3, only the drain valve and drain pump will on, other operations, other 1, 2, 3, 4 operation must be off. So like that, you have decided the pattern. Now what you have to do, why this pattern has to be identified? Because once the pattern has to is identified, then you will write this pattern to a corresponding register. So we have chosen 11 register, that is HR251 to HR261, where in each step, to perform the each step, we have written the pattern. What the pattern? So here it will be 0 0 0 0, and this will be 1, and this will be 0. So you see it is 0 0 0 0, and that this bit is 5th bit is 1, and all others are 0. Okay, because it is a 16-bit register, so we are only using the 6th bit. Okay, because 11 up to 11 we have to go. So like that, for each cases we have written the pattern in the corresponding register. Okay, and we want to transform this pattern to the output group register. Suppose that we have fixed output group register 2. Okay, so now we want to develop the programming. Okay, so there are 11 steps, so therefore we need 11 register to control the pattern. As I said, on the right of the figure, the required register pattern for the correct dishwasher sequencing is shown. The 11 HR bit pattern are programmed to match the required on-off pattern of each step. Only the first 6 bits of the 16 each registers are needed in our illustration. Okay, and now another thing has been specified, that a more complete program for our dishwasher control will be useful if we programmed the time of 140 seconds. I mean, suppose each of the steps are going to perform for 140 seconds of time. Okay, actually in the dishwasher operation the time would be obviously much longer. For an example, suppose each step we want to perform for 140 seconds, and then it will automatically goes to the next step. So additionally, there is a start stop button to enable the sequence to stop at the end of the 11 steps. Okay, so let us try to understand the programming, then we will come to the discussion. Here is the programming. Here you see we have used a logic CR39. So there is a push button switch IN001. So once the IN001 is pushed, then stop button is already closed, then what will happen, CR39 will be energized. But if it is released, then what will happen, the CR39 is in latching operation and DR40 is normally closed. And now you see what is DR40. DR40 is the coil for the sequencer function. So here we have written steps 12, but we want to perform only 11 steps. Why we have written 12? I am going to discuss that one. So why 12? Fine, but the rest of the things let us discuss. First, you see the step what we have used, that is the address of the timer TS41. Let us see what is TS41 is coming So here you see TS41 is a timer, and we want to generate a pulse at every 140 second interval of time. So that's why the preset value we have taken 140, and the CR39 is the master switch, so that's why the reset and enable as well as the run switch for the timer we have taken the address of CR39. So once we know that the DR40 is going to be energized at the 11th step. Okay, so sorry, it is going to be energized at the 12th step. Okay, at the 12th step. So until the 12th step it is going to be de-energized, so that's why it is going to be normally off. So what will happen, whenever you will push the start button, then CR39 is going to be energized. Once it is going to be energized, then it has been latched using this logic. And once it is latched, this CR39 here, it is also energized, this is also energized, and this is also energized. Okay, and the same CR40S41 is used as an enable reset. We know this, why this has been done, because we want to generate a short spike at every 140 interval of time, okay, or second of time. So now what will happen at first step, at after 140 second of time, this has to be pulsed. Once it is pulsed, then what will happen, the beat pattern means it will move from the H at 251 to H at 252. Okay, so like that, what will happen when you will reach at the 11th step. Okay, when you will reach at the 11th step, the 11th step function will be executed, and at the 12th step what is going to happen, this CR39 is going to be false, and then everything is going to be reset. And what will happen, again the pointer is going to start from the H at 250, so the things is going to be repeated. Okay, so here thing is that instead of 12, if we will write 11, then what will happen, at the 11th step CR40 is going to be energized, and if the 11th step CR40 is going to be energized, so then what will happen, at 11th step this DR function is going to be reset. So to avoid that, what we have done, we have taken 12 steps such that up to 11th step it is going to perform the steps, and 12th step what is going to happen, it is going to activate, and at that time it is going to reset. So this is why we have taken, instead of 11, that is 12. This is as simple as that, the way we can perform this sequencing operation for the to control the dishwasher problem. Okay, but suppose the requirement is little bit different now. So previously every equal length of time we are going to execute each of the functions, but it may happen that it is requirement is something like that each function has to be executed in a different time interval of time. Okay, so how we can deal that one? So you may also want each step to have different times. So first case what we are taking, it is little bit typical case. What is that? If the times are all multiples of 4 seconds, you can use repeat registers and lengthen the program. So suppose each and every steps are the multiples of 4. Means our step 1 is 4, step 2 is 8, then again the step 3 is 4, then step 5 is 12 seconds, like that. Then if this kind of pattern is there, then how we are going to perform the operations? Now that can be done by what it has been shown that you can use the repeat registers. How? Now previously you see our time length was equal 140 seconds, so that's why we have taken 11 registers where the patterns were written. But now what I'm telling that we have a provision that we want to execute each of the steps, that is multiple of 4, something like this. Suppose we have fixed that 11 steps will be something like this. That first it will be 8, first step will be 8 seconds, second step will be 4 seconds, third step will be 12 seconds. So like that we have fixed it. Okay, suppose 11 step will be performed for 28 seconds, so all are multiple of 4. So now what you can do, that the previous so to execute the same functions or same steps for the 8 second, that suppose step 1 has to be performed for the 8 second, then what we will do, we will use at that time 2 register address, that is 251 and 252, and we will write the same pattern. If you will write the same pattern, what will happen? If you use the preset value 4, okay, for the timer, then what will 4 second, if you take the preset value of the timer, then what will happen? The first 4 second, what will happen? 251 will be executed, and then again after 4 second it will be pulsed. So then the control will move to the 252, but 252 again the same pattern has been written. So it means that 4 plus 4 total for the 8 second the same function will be executed. So the second step is only the 4, so only one register we have taken. But for the 12 second means we have to take 3 register, that is 54, 55, 56. Same pattern has been written. So in this way, what will happen? The number of registers you have to take and the number of length also will increase. So here you can say that to execute this all 11 number of steps, we require actually required to perform total 28 number of steps according to the requirement. So that's why the same thing will be there, same programming will be there, the same programming, only here you will write 4 second, okay. And here only the changes will be there. What the changes will be there? Now the steps will be, you will find that instead of 12 we will write steps 28, and the starting register is 251, pointer also 250, and then OG is 002. These are the changes you have to make. Okay, so this is the one possibility. Now because you see we require 27 registers, and that's why we have written here number of steps are 28, one extra. Fine. And now suppose if you want variable time instead of multiples, you would use 2 sequencer operating together. Now suppose somebody said that no, we do not have particular typical for multiple of 4 seconds where the problem has been solved in this way, but we want that each and every steps may have different timing, completely different timing instances or duration. Then how we are going to perform that? Then what we have to do, we have to use 2 sequencer functions at that time. So one sequencer would step through one group of registers for output patterns, and other would step through registers with the times. The times would be sequentially fed into the step timers time interval registers. A system for variable interval is shown in the figure. Okay, so the same dishwasher problem we are showing. So now what will so previously what we have done, the fixed timing interval 140. Okay, but now what this step we will not write. Okay, this step we will not write. Up to this it will be same 12 steps we will write, to execute 12 number of operations or to 12 number of steps. But along with that, you can along with this, instead of this timer, we have taken another timer whose preset value is no longer constant. It is a address of the register HS401. Okay, and from where this value will come? The value will come from the another sequencer functions what it is used, where the 12 we have written the 12 steps, and the address of the preset registers are the destination address of the sequencer function. Okay, now whatever the timing sequence you require to execute the each step, you write that corresponding registers, that is HR351 to 11 number of registers, that is HR362, maybe 40 second, 50 15 second, whatever the requirements that you write in the memory or in the registers of HR351. Okay, 351 to 362 11 registers. Okay, so now how it is going to work means, try to understand that this is connected here. Okay, and this is connected here. It is a continuation. Okay, now whenever the IN001 is closed, then 39 is energized. So 39 is energized means this is energized, this is energized, this is also energized, this is also going to be closed, this is also going to be closed, this is also going to be closed. Once it is closed, then if here you see for the step the address of TS41 is given. Okay, and here also for another sequences TS41 is given. So whenever this is on, then TS41 will be energized. Once it is energized, the first step 251 will be performed. Okay, and 351 will be performed, and then it will move to the second step. And in the second step, what will happen? Now in the second step, this preset value will be read from the content of 352, that is 15 second. Once it is set for the 15 second, then what will happen? After the 15 second, this CR41 is going to be energized. Once it is going to be energized, then it is going to pulse this pointer as well as this sequencer as well as this sequencer. Then what will happen? It is going to move from 252 to 253, and here also it is going to move 352 to 353, and you have to see HR353 what the time is written, and accordingly this preset value will be read by the timer, and it is going to execute the operation. So in this way, the variable timing can be we can use the variable time to perform this sequence of operations. Okay, so I will stop here. Thank you.